Okay, so let's get started. Just 1 second. So welcome back. We will start a new topic today on consistency and replication. Before I do so, I wanted to make a couple of announcements. We have put out the exam grades, right? So what we will do is we will add the solutions to Canvas later today, and then tomorrow we'll open the regrade window. So take a look at the solutions, and if you have questions, you can of course submit a regrade request. By and large, the class did fine. I think it's just the same as what we have seen historically. The mean and the average tend to be in the low 70s, so it was 70.5. So it's no different from what has happened in many years. So I think that the performance of the class is pretty good, in line with historical averages. So I don't think there's anything vastly worrisome or anything like that. But still, if you have questions about anything, you should come talk to me. Okay, it's not a problem. All right. So what I'll do is I will continue our discussion from last time. We will switch now to consistency and replication. Last time we were talking about distributed transactions. If you remember, I mentioned what transactions are, what acid properties are, and so on. And we'll continue from that point on. Today, we'll focus more on consistency aspects. Remember last time when we were talking about transactions, I mentioned consistency. We'll look at that in a more detail, but more in the context of replications and transactions. We'll look at data-centric consistency, client-centric consistency, and then we will end with eventual consistency. Okay. So let's start with replication and try to understand why we need to have consistency, right? So replication, as we have seen, comes in two flavors, right? One is you replicate the data that's part of your distributed application, or you replicate the computation, where the code itself is replicated and is running on multiple machines. So today we are mostly concerned about data replication. So whenever you have replicated the data in your distributed system, there's multiple copies of the data. Okay. So and the reason that you have to keep these multiple copies is, number one is reliability. If one machine goes down, and all of the data on that machine is lost, there are other machines with other replicas that you can use. So the data as a whole continues to be available, or if there's data corruption, it continues to be available. Okay. So that's reliability. The other is performance. So when you have multiple copies, you can then take your request workload and split it across machines. That allows you to scale your application up with the size of the distributed system, or you can put these replicas in different locations and then have the request go to the closest replica. That's called geographic replication. Some of this will come back to when we talk about the World Wide Web. Okay, but today what we will do is to actually look at a problem that comes up whenever you have replication, which is that of consistency. Okay, but before we do that, I do want to mention 2 or 3 other questions that we will actually look at when we come back to the World Wide Web discussion. The first one is trying to think about when you want to replicate your data or computation. Second is, if you want to replicate, how many copies are you going to make? Where should the replicas be placed, and so on. So these are all issues that are related to replication that we will table for the moment and come back to. Okay? But for now, we will talk about consistency. Okay, what is the problem of consistency? Whenever you have multiple copies of the data, if one copy is modified, you want to ensure that other copies are in sync with the modification. Otherwise, some replicas become stale and others have more up-to-date information, and that's a problem. Then if you go to a stale replica, you are getting an old version of the data. Okay, so you want to ensure that all of the replicated information in your system is consistent with each other. Okay, so that's the problem of consistency of data. Okay? And as we start talking about it, I want to start with the very well-known theorem, excuse me, in distributed systems. It's called the CAP theorem. Okay? CAP is an acronym that stands for consistency, availability, and partition tolerance. So that's what CAP stands for. But what is the theorem? So first thing is, it was proposed by a professor at Berkeley. His name is Eric Brewer. Is very well known in distributed systems. And what he conjectured at the time, it was not a theorem, it was more of a conjecture, but later on, I think it was proven to be true. Okay, but what he conjectured is impossible for a distributed system, or he referred to it as a web service, but really is a distributed system, to provide all three guarantees at the same time. Okay, you want your consistency guarantees, which means that if there are replicas, you want all the clients to see the same data, which means most up-to-date data. That's a good property to have in your system. You want availability. Availability means if some nodes in your system fail, the system as a whole continues to function, so that small number of failures do not bring down the system. Another desirable property, okay, of a distributed system. And the third one is partition tolerance, which means that the network can lose packets. The network, in this case, there are network failures, which means that some packets can be lost. Again, you want to tolerate that as well, right? So in some sense, if you build a system, you would like your system to provide consistency to your clients. You want the system to have good availability so that node failures don't bring the system down. And you want to tolerate network packet loss. And what the theorem says is you can't have all three in your system. Okay? As you design the system, you have to decide which two are more important to the application, and you have to pick two of the three properties, because it's impossible to have all three properties at the same time. Okay? That's what the theorem says. Now, this is important when you're designing larger distributed systems. You got to ask, is consistency really important? Is availability more important? Should you tolerate network outages and so on? And decide which of the two you want to put in your system, because any system that you build, by definition of this theorem, cannot actually have all of these three properties which you would like to have. Right? So here are some examples of systems we might have talked about briefly, and we'll see which two of the three properties they chose. The first one is consistency and availability. So you're picking the C and the A, but you are giving up on network partition tolerance, which means that you cannot, if there are network problems, then the system will actually have issues. So these examples of this would be things like databases, okay, where you don't actually deal with if the network problems, cluster databases. We didn't talk about LDAP in this class, but we will talk about XFS, that's a file system. We'll get to when we talk about file systems, and two-phase commit is actually coming next time. But at least databases actually give you consistency guarantee. Their asset properties, they might give you availability properties, but they give up on network partition tolerance. Okay? Now, if you look at some other systems, they made other design decisions or choices. So if you take distributed locks that we talked about last time, okay? Now they had consistency. They ensured that the lock state is consistent. We saw that if the network goes down, they can actually deal with some of this. But if a node goes down, like the node lock master goes down, you are out of luck. Right? That's what we talked about. So some of the locking protocols we talked about do not give you availability guarantees, but they give you these other two guarantees. Okay? And there are other systems, like we'll talk about web caching and so on, which don't give you consistency guarantees. They relax consistency, but they give you availability and partition tolerance. So you can deal with nodes going down, you can deal with network going down, but you can't ensure consistency, because fundamentally, if you partition the network into two, okay, you can't keep the replicas in sync anymore, because they cannot talk to one another. So you have to give up consistency in that. Right? So these are just examples. We are not going to go into a lot of details here, but you would need to know that this property of distributed system, which is very fundamental, actually exists. And typically, you will see the CAP theorem actually shown as a triangle with three properties, C, A, and P: consistency, availability, partition tolerance. And it's basically says pick two when you design your system. Now, this picture here actually shows you all kinds of databases that you can get. Like you'll see things like MongoDB and Cassandra, Dynamo, relational databases. Excuse me, and you will see what choices they have made. Okay, different databases have made different types of choices, but the same is true for more general distributed systems. Okay? We don't need to go into the details of what each of these mean and what they are doing. What you really need to know is that there is this property called the CAP theorem, which basically is an impossibility result. It says that it's not possible to have all three of those desirable properties in any system, and when you design the system, you have to give up one of them, and you got to decide which one is the one you want to give up and which are the other two properties you want to keep. All right. So that's a consistency theorem. But now let's actually talk about consistency techniques. Okay. Excuse me. So the first thing is we got to start with the basics. The basics is say that we have replication in the system. Our data is replicated. Here it says objects are replicated, but really it means the same thing. Okay. Now, who handles the replication? It's not really important for the consistency discussion, but later on when you talk about replication, we'll see it becomes important. You can either put the burden of replication on the application, okay, or you can have the system deal with it for you. Okay. We'll talk about some aspects of cloud provisioning where cloud systems are going to deal with replication, but in other cases the application deals with it. Okay. But either of these two entities are going to decide what to replicate and how much to replicate. But regardless of who makes that decision, consistency still has to be handled, and that's what we are going to talk about. How do you deal with consistency? Okay. So to understand this notion of consistency, I just want to take a step back and have you think a little bit about replication, okay? And you'll try to see under what scenarios it actually even makes sense to replicate. So here's a very simple example. Let's say you're building some application. Okay? Maybe it's for your lab. Lab 3 will actually involve replication. So you will have multiple copies of your data or multiple copies of your application. Okay? Now you can ask, does having these multiple copies actually give you benefit, okay, in terms of performance or something like that? So the way you will think about this benefit is replication is going to come at a cost. The cost is the cost of maintaining consistency. Okay, so you are going to pay some extra cost, extra messages have to be exchanged to ensure that data is consistent. That's the cost you pay. Okay? And the benefit of replication is, of course, now there are more copies, so you can service more requests. Okay? You can scale up. Okay? That's a benefit. So you can do a very simple cost-benefit analysis to see under what scenarios is the benefit of replication going to be greater than the cost of consistency that you have to pay for that replication. Okay? So that's the question. And here is a very simple example. Okay? Let's assume there is some data or object that is replicated n times. N is some number greater than 1. Okay? Now we'll assume that this data item is read with some frequency r, which means that it's getting accessed with some rate r, but it's also being modified at some rate w. Okay? Now the modification, the write frequency or the modification rate is directly related to the consistency overhead. Every time you write to one of the copy, you have to send messages to other copies and propagate that update so all the copies are in sync. Okay? So if W is your write frequency, the cost of consistency is directly related to W. Okay? And the read frequency is basically the benefit you are seeing because you can then send your read request to different replicas and scale up. Okay? Now, if you have a case where the read frequency is much smaller than the update frequency, which means that the object is updated a lot, but it's read infrequently. Okay? So in this case, you will see that the cost of consistency is high because that's the write frequency. Okay? So you are going to be writing it frequently and then sending all these messages to keep the replicas in sync. So there's a consistency cost you paid, which is directly proportional to W. But the benefit is very small because you're writing a lot, but no one is accessing that data that's being updated, right? So in this case, actually, it says that probably the replication is not giving you the benefit you want because the write frequency is much higher than the read frequency. Okay? But if the opposite is true, where the read frequency is much higher than the write frequency, then what it says is every time you update it, the data item, and then you propagate those updates to all the replicas, you will have lots of reads that access that data item. So you have actually recovered the cost of sending all these messages through lots of read requests that you service later. Okay? So if read is much greater, frequency is much greater than write, then you can actually get the benefits of replication because the consistency overhead is much smaller than the benefit of having all these reads. Okay? But in the opposite case, it's not true. Okay? So in some sense, what this very simple analysis is showing is, yes, replication gives you benefits, but it comes at a cost. The cost is consistency overheads. Okay? And then that cost is not negligible. You have to weigh that cost against the benefit of replication. Okay? Okay, so that's the analysis. Now, I said the consistency cost is related to W, but what it is exactly will depend on what type of guarantee you give, and that's what we are going to look at. You will see that depending on the type of consistency guarantee, that cost can actually vary. It's always related to it's always related to W, proportional to W, but in some cases higher than other cases. Okay, so now let's start analyzing what is the consistency guarantee you want to provide, because the stronger the guarantee, the higher that cost is going to be. Okay, is that clear what I said so far? Okay, so let's start with some basics. Okay, so first thing is we'll use this term consistency semantics, and that just means what type of guarantee you are going to provide. Okay, what does that guarantee mean? So this is the picture you want to keep in mind. So there is some data that's stored on these disks, and you'll see that there are multiple disks, so the data could be replicated. Okay, there are some applications that are accessing the data. Any application can go and access the data from any of the replica. Okay, you'll see in this case there are 3 replicas. So this process here accesses the first one, that process accesses the second one, and so on. Okay, and then the question is, when a process tries to access data, what is it going to see? Okay, in terms of what is the guarantee that the data store is going to provide in terms of what you are going to see. Okay, ideally you want any of these processes to see what are called the results of the most recent write, which means that you have to see the most recent update. Okay, that's the most recent copy of the data or the file in the system. Okay, so that's what you would like, but you will see that the definition of what is the most recent update itself is actually a tricky question, and that will give us a range of different semantics, that some of which are stronger than others. Okay, and so let's start talking about what these guarantees are and how you can think about their costs relative to one another. Because the simplest approach is what we will call strict consistency. Okay, excuse me. So as the name strict consistency suggests, okay, a read request will always return the most recent write, regardless of which replica you go to. Okay, so it means, in some sense, this means you will never get any stale data. You are keeping all the replicas strictly consistent with one another. So anytime there's an update, all other replicas are immediately updated. So whenever any other application tries to read it, they always get the most recent version. They never get anything stale. Okay, it's called strict consistency. Okay, now seems like a good property to have, but as you will see, this one is actually the most expensive, and in some cases you will see that it's not actually possible to even guarantee strict consistency. The first thing is, it's implicitly assuming a global clock. Okay, it is because you have to ask, if I send a read, what is the most recent write? It requires that you be able to compare time across machines. So if the most recent update happened at time t, okay, and then some other machine is seeing a read at time t plus epsilon, those 2 machines have to be synchronized. Otherwise, you don't know what is the most recent write. Right? So you need to know that. So implicitly is assuming that your tight synchronization, which you already seen, is impossible. Right? But let's, for the sake of argument, assume that you have the perfect synchronization algorithm. Okay? Every machine is tightly synchronized, so you can figure out when there's a write, the next read needs to return that version of that object. Okay? So let's assume that. Okay? But there is now a second problem, which is that the strict consistency semantics require that updates are instantly propagated to all machines. Okay? Let's say the update to a file happens at noon. Okay? Maybe 1 millisecond after noon, there is a request for that file at some other replica. Okay? Now, strict consistency says that the read, which happened 1 millisecond after noon, okay, should get the update that was made at noon. But what if it takes 10 milliseconds to propagate this over a network? Because network latencies are finite, they are not instantaneous. Okay? So it might take you some time to actually send that message. Messages are not going to reach instantly. Okay? So now, if it takes you longer to propagate the message, you cannot fundamentally even guarantee strict consistency, because 1 millisecond after noon, there is no way the message would have actually reached that other machine that it has the most recent update. Right? So as you can see, because you can only propagate information at speed of light, that's the speed at which you send data over a network, okay, that's still finite. There's always a finite delay between when a write occurs and when you can send the message. What if a read comes before the message has actually reached? You cannot guarantee strict consistency in this. Okay, so in some sense, this is a good property to have, but in practice, there are lots of problems. First, it requires clock synchronization. Second, it assumes that a write is immediately visible, which means you can propagate updates with latency 0. That's not true. In real system, there are actual network delays. So this is hard to actually implement in practice. Okay? But it is the strongest guarantee you can provide to any application. So now we'll start relaxing this to try to get other properties that are good properties, but not as strict consistency. Is this clear? Any questions here? Excuse me. So next property is called sequential consistency. Okay? This property is one step weaker than strict consistency, actually 2 steps, but for now we haven't seen others, so this is going to be weaker than strict consistency. Okay, so now we are going to start thinking about reads and writes and what writes are visible to what processes and so on, and you will see why this is weaker. Okay, so the first thing we'll assume is there are n processes in the system. These processes are reading and writing some shared data that's replicated across machines or processes. So we'll assume that all within a process, okay, operations are executing sequentially because that's sequential execution. So maybe there is a read from a file and then write to a file. We'll assume that the process is actually executing them sequentially. So those reads and writes are ordered based on the order in which they appear in the program. Okay, that part should be clear. Okay, and then we will assume furthermore that when you have multiple processes, their reads and writes are going to be interleaved rather. Any valid interleaving will be allowed, and all processes have to agree on the same interleaving. Okay, that preserves program order. Okay? So here is an example for you to understand what all this means. Right? So here are 2 small pictures at the bottom, okay? And there are 2 different examples. So there are 4 processes in this case. Okay? There is a single shared data item that's replicated across processes, which is called X. Okay? You will see in this case process P1, okay, so this thing WXA simply means that process P1 wrote A to X. Let's say X is a file. Very simple, right? X is a file. So you essentially write A to the file. Okay, so you have now written A to the file. Process B goes and writes B to the file. Okay, so and you will see that if x-axis is time, in this case it looks like the A operation, A write has happened before the B write. Okay, now all processes have to somehow agree on the order in which these writes have occurred, and they have to see the writes in that same order. So if you assume, okay, this process is decided that the B write has happened before the A write, okay, that's allowed as per sequential consistency. And then when you read it, you will first get B, okay, because you see that write first, and then you will see A because you see the second write later. So you actually see them in the opposite order. Okay, and that's allowed because you are agreeing to that interleaving and everyone sees in that order. Okay? If this is a strict consistency, this would not be allowed. You would actually see the first write because that occurred first, that would propagate, and then you would see the second write. Okay? We have relaxed it. We said maybe since strict consistency is impossible, let processes decide. Okay? Maybe this P2 is closer to P3 and P4, so somehow its write appears, that message appears first. Okay? And that's allowed in our case because we are not asking for any strict synchronization and so on. Okay? What is not allowed as per strict consistency is where 2 processes see the writes in 2 different orders. So in this case, P3 sees B and then sees A, and P4 sees A and then sees B. So that is disallowed. Okay? You want to agree on some order of these writes, and every process has to see them in the same order. Okay? And whatever you picked is okay so long as you all see them in the same order. So the second case here is not sequentially consistent because you're seeing things in different order. Okay? So it should be clear how this is different from strict consistency, because we could say B as the right to B, the B write happened before the A write, even though in time order it's the opposite. A strict consistency would have only allowed one order. Here we are allowed either one, and then once you agree, everyone sees that order. Is that clear? Okay. So this is called sequential consistency. You will see it's now a relaxation of strict consistency. Okay. Next, we'll talk about linearizability. Okay. So this is a different a different guarantee. Okay, it seems somewhat like serializability that we talked about last time when we were talking about acid properties, but they actually are two different things. They'll sound similar. Serializability in context of transactions simply says the transactions have executed in some sequential order and the output is based on that order. So it's really related to transactions. Linearizability is a consistency guarantee, has nothing to do with transaction. Okay, so it is now actually you will see that it is a stricter guarantee than sequential consistency, which say that linearizability assumes sequential consistency. Everything we said before holds. And what also is true is if timestamp of operation X is less than timestamp of Y, then X should precede Y. Okay, so let me show you an example. So in this case, okay, you have two writes. Okay, now there is no message between these two processes between those two writes. So these writes are concurrent. So you can order them in whatever order you want. But if there was a message that went from P1 to P2 between those writes have gotten ordered. Okay, this is basically what we did in Lamport's clocks, if you remember. Okay, because the send is preceding the receive, the write precedes that send, and another the receive precedes the write. These two writes get ordered based on timestamp order. Right? So what this is saying is, if there is some message or there's any way to actually relate these two writes, you got to respect the order. You can't invert it. Right? So if there was a message here, then you should have always seen A before B. You cannot agree on B before A. Okay, is that clear? So that's what linearizability does. But I'm going to give you another example. So what does it mean to send a message? Okay, so here's an example of an implicit message. Okay, you write A to X. Okay, process P is going to read that shared data X and is read A. Okay, and then it writes B. Okay, now this is not an explicit, this read is not an explicit message, but it is a implicit communication between P1 and P2, because P1 wrote A to a shared buffer. P2 read that shared buffer and got A. That's equivalent to you sending a message implicitly, because some information has passed from P1 to P2. Okay, so this read here between these two writes actually causes these two writes to get ordered. Okay, even though that's not you can't have an explicit message as per Lamport's clock that will automatically order those writes, but you can have implicit communication where you are reading that shared data. If there's a read between two writes where you're reading the same shared data, that's communication as far as we are concerned. Okay, so these two writes are going to get ordered. So what that means is all processes have to see if you are linearizable A followed by B, and here you see one sees B A and other sees A B. That's disallowed as per linearizability. You actually have to see A B in both cases. Okay, all right. So that is our linearizability, which is saying that you have to have all the for sequential consistency, but if there is any way that the timestamps can be compared between two of these operations, then you have to ensure that that order is preserved. Okay, so there is another example here which I will not go into as much detail. It's trying to say the same thing, which is there are three variables that are shared, X, Y, and Z. Okay, and then what you do is you set each variable and you print the other two. So that's a way to communicate between changing the value and then reading that value. So that's the write, that's the read. And then it says that depending on what is printed, what is allowed and what's not allowed. In this case, actually all of these sequences that you see, the interleaving of these messages, or not messages, instructions rather, are linearizable. And I should have started with the actual programs. There are three processes, okay? P1, P2, P3. This process says X is equal to 1 and reads Y and Z. That sets Y and reads the other two, and that says Z. So each of them is changing one of the three variables and then reading the other two. Okay, so that's essentially message exchange between these processes by accessing shared data structures. And then that's the linearizable schedule that says that these are different interleavings, as you will see, of those 6 instructions. And this is what each of those print statements produces. All of those are linearizable because once you set a value, all subsequent print messages actually see that value. That's what it's saying. Okay, because that's the ordering. Okay, but the other example I gave you is actually easier to understand from a linearizability perspective. Okay, So that's linearizability. So it's strict consistency. That's the strictest. Linearizability one step below. Sequential consistency is one step further, because you will see linearizability is stricter than sequential because it does everything that's sequential and it has an additional condition that makes it stricter, not looser. Okay. All right. Next one is called causal consistency. This is almost like linearizability with one difference, which says what causally related rights must be seen in the same order. But if there are concurrent rights, you don't need to agree on an ordering. You can see them in different order. Okay? In sequential consistency, you have to always agree on order, whether they are consistent or not. In linearizability, if there was a causal relationship, you actually had to respect that causal. You couldn't invert the causal relation. Here it says only respect causal relationships. Other operations can be seen in different order. Okay? So here is an example that I already showed you. So you have two writes that are causally ordered because there's a read between them. This read is seeing what that write wrote and then doing another write. So these two writes get causally ordered. So you have to respect that ordering. If you're causally consistent, you should always see A followed by B. Okay? Here you don't. You see B, A, and A, B. So this is not permitted as per causal consistency. Okay? Now, if I remove this read, okay, those two writes are now concurrent because there is no message exchange between those two processes. Okay? If they're concurrent writes, we say we don't care anymore about the ordering. You are allowed to see BA and AB because they're concurrent. We don't actually require you to have any ordering at all. Okay? If this was sequential consistency, even if they were concurrent, you have to agree on something. It would agree on A, B, or BA, it doesn't matter, but you have to agree on something. All processes have to see those rights. Here, you can see them in different order. Is this clear? I mean, it's kind of little bit complicated to understand, but once you get the basic idea, then it's clear what's going on. Okay. So yes. Yeah. So question is, when you say write A and B, are you appending to a file? Are you modifying it? Both of those are acceptable, right? We are just modifying some shared data item. Okay. You could append and modify it. Like if you have a file, you can open a file and literally write A to the file and save it. And then you can write B, which either overwrites it or appends it, doesn't matter. You just created two copies, right? One is before the other. Okay. And you could do that to a database as well. So it's just any modification is fine. We are just talking about modification. Yes. So what does the ordering mean? So, I mean, if you want to think about it, here is a very simple way to see it, right? So let's say you have these two processes. I'm going to make a different example. Let's say that is you and your lab partner are working on the same file. Okay? You opened your file in your browser, you go and write the letter A to the file, you save it. Your lab partner writes B to the file or modifies it or something like that and saves it. Okay? Now here's a third machine, which could be your build machine. Okay? So then the question is, how do these files become visible to the build machine? Which of these versions does it see first? Okay? That's an example of causal consistency. Now, in this particular case, what has happened is you wrote A, your lab partner actually read the file and it saw your changes and then made another change. Okay? This means it's causally consistent because your change got propagated and was seen and then modified again. So in this case, that all these other machines should always see your update before the other update, because that's causally consistent. But in this case, there is your lab partner is not reading your file. You are making changes independently of your lab partner. So you made changes to the same file. In this case, different machines can see those updates in different order. Okay? Even though as per time order, you will see if this is time, this change has occurred before that. But we don't care about that as far as sequential causal consistency is concerned in this case. Is that clear? What we are saying? Yes. Any other questions here? Okay. So that's causal consistency. So there are many other models. We will not go into this. There is something called FIFO consistency that's even looser, which says writes from a process can be seen by others in the same orders, but you can have writes from different processes seen in different order, which is basically saying you don't even need to worry about causal relationships. You can see writes in different order and different machines. So it relaxes that and so on. So we started with strong consistency. We ended with something called FIFO consistency, which I just talked very briefly, didn't go into the detail. But each of this is trying to relax this notion of strict consistency because it's very expensive to maintain. All of them involve sending messages to update the shared data item and replicas and so on. Okay? So that's something you want to keep in mind. Now, there are other ways to think about consistency that don't look at individual reads and writes. Instead, they look at critical sections and try to make databases or files consistent across boundaries of critical sections. So assume now that before you make a change, you grab a lock, okay? You make some changes, and then you release the lock. Okay? If you have this model, then between the acquiring and the lock and releasing the lock, whatever changes you make don't have to be propagated. You wait until the lock is released, and then you make all the changes visible at once. Okay? This is what databases also do. If you remember when we talked about transactions, there's a begin transaction and end transaction, and you really only when you commit the transaction do the changes become visible in the database. Otherwise, you can throw out the changes. Right? So these types of techniques which operate at granularity of critical sections do the same thing. Say rather than worrying about reads and writes, which is too complicated, let's assume there are abstractions like transactions or locks. Okay, so you have either at the entry point you make everything consistent and then grab the lock, or at release time, which is when you release the lock, you then propagate all the changes. But between the entry and the release, any changes are local. You're not even sending them out at that point. Okay, so that is going to actually simplifies how often you have to implement consistency and send updates and so on. Okay, it's one step weaker than doing this for each read and write operation. Okay, so there is, as you will see, a sequence of these things. Okay, you don't have to know every single detail about all of these, but we started with strict. We talked a little bit about linearizability, sequential consistency, causal consistency. Then I said a little bit about FIFO. So you're weakening these guarantees, and then you go to these other consistency models where you have weaker consistencies guarantees at the granularity of acquiring and releasing lock. Okay? So that's a spectrum of approaches. Okay? Which one you pick actually depends on your particular application. Okay? And we'll see that many of the systems don't even do any of these. They do something even weaker than this, as we'll just see. Okay? But it's good to know that yes, I mean, strict consistency looks great, but there are other things you can actually have in your application. Linearizability is something that you will see is somewhat common in some applications that want stricter guarantee. But strict is almost too hard to achieve in practice. Okay. All right. So I'm going to say one more thing, and then we'll talk about a much weaker form of consistency, which we'll call eventual consistency. Okay. So this model here is called client-driven consistency. It says rather than thinking about consistency from the perspective of the database or the shared file storage or the shared storage, let's think about it from the client perspective. Okay? Can we reason about the correctness of what is being data is being made visible from the perspective of the client? Okay? So what does this even mean? Okay? So what this says is if there is a client machine, a laptop, say, I'm going to show you. Okay, so let's say there is a laptop. It basically makes a read of some data item and it gets a copy. Okay, we will assume for sake of argument the laptop moves to another location. Okay, then it does another read, and potentially this time the result is returned from a different replica in the system. Okay, what is it that the client should see? Okay, and the basic idea is after you see something, say see some data, you shouldn't go to another location and see older data. That's bad because you already saw something more recent. You go somewhere else, you see older data. That's actually disallowed, right? So that is what monotonic read says. Monotonic read says once you read some file, you shouldn't go to another location and get an older version of the file. Okay, that's not allowed. Okay? Monotonic write says once you update a file, okay, you shouldn't go to another location and see something older. Okay, that's monotonic. So writes and reads are monotonically becoming newer. You never see older versions of it. Okay? Read your write says, let's not worry about multiple clients. Okay? At a minimum, if you read something, then if you wrote something, you should at least see your changes. Maybe you will not see changes made by others, but at a minimum, you should see your change, right? So you updated your file. Okay, this actually happens quite commonly. Maybe you updated the file is still uploading to the cloud. You go to another device, you try to access that file. Since it has not synced with the cloud, you might see an older version, right? So in this case, you are not reading your writes. Okay? It happens very commonly because cloud systems don't update immediately. So you can see this happening, right? You can, if you use any system like OneDrive or Dropbox or any of this, you can make a change on one device. Okay, while it's uploading, if you actually open that file on another device, because your sync hasn't happened, you will see an older version. That is not allowed as per this. You are not seeing your own updates, let alone other people's. So these two things says you're seeing updates across client. This one is saying you should at least read your writes, or write follow reads basically is the opposite. It says that a write following a read will take place on more recent versions of X. At least you're saying you can update your own copies and see them in the right order. Okay? So these are consistency techniques that are not looking at the problem of consistency, the perspective of the system. They're looking at it from the perspective of the user. Okay? And at least the user does not see inconsistent information. Once you read something, you go and start seeing older ones. Now that actually happens quite often as in many scenarios. One example is if you go and update your password sometimes, okay, on one device, okay, and then you try to log in to that account on another device, sometimes the password has not propagated. You actually will see you have to use your older password to log in, because the databases, there are multiple copies of the databases, they have not synchronized. One of them has seen your password change, the other one has not seen it. So you try to log in with your new password a few seconds later, and it says that the password is incorrect. Okay? So these are all examples to show that even these very trivial properties, many systems don't even support. Okay? You will see all kinds of inconsistencies occurring as a result of all this. Is that clear? Okay. So we will now get to the last part. You had a question? Okay. We'll get to the last part, which is called eventual consistency. Okay? So eventual consistency basically says that everything we talked about is too complicated, okay, too expensive for the system, so we'll not give any guarantees. Okay? What we'll assume is that you make changes to the system, those changes will propagate to other copies. Okay? It will take a while. Until then, things will be inconsistent, and that's okay. Okay, this is why it says eventually things will be consistent. There's no guarantees on how quickly changes will propagate, how much time it will take, but that's okay so long as we do this in a best effort manner. Okay, we live with all the inconsistencies. Okay? Now it turns out this sounds like almost silly, right? That you are not giving any guarantees and you just say it's too bad, things will be inconsistent. But that's what many systems actually choose, because they find that whatever I talked about is all too expensive. So why give any guarantees? Let these things happen in their own time, and things will get consistent eventually. Right? So that's the basic idea behind eventual consistency. Practically all of the systems that are mentioned here, domain name system, password databases, cloud storage, all eventual consistent. Right? So you can take any cloud system, this iCloud, OneDrive, Dropbox, they give you no guarantees. You make a change, it may take minutes for you to show up on some other device, because they're not giving you any guarantees. They are making the best effort to update all the replicas, but no guarantees are given. Right? So many systems have taken this approach and said it's too expensive to do anything more, so we will not give you any guarantees. You have got to live with all of the inconsistencies, figure this out yourself. Okay? So now we'll talk about, although this sounds somewhat trivial, there are actually protocols that allow you to implement eventual consistency. We'll see how to implement them. All of what I discussed are just definitions, right? Strict consistency, linearizability, they're all definitions. I didn't say how to implement them. Okay? But at least for eventual consistency, we'll discuss how to go and implement these ideas. Okay? So that brings us to a little bit more of definition, and then we'll see implementation. Okay, so here for eventual consistency, we'll assume a replicated database. Okay, here's an example for replicated database. There are many copies. There's a network in between. Okay, anytime you make a change, we'll assume that the databases will try to propagate those changes to other replicas, but there is no guarantee on how much time it's going to take for them to update, how frequently they'll update. Eventually, these updates will get pushed. That's the basic idea. The update will eventually propagate to all replicas, so it's very cheap to implement. Okay, and we'll see how to implement it. Okay, so that's the basic idea behind eventual consistency. Okay, so the popular approach to implementing this is called epidemic protocols. Okay, so this idea was designed, I think, in the late 80s in a system called Bio, which was at that time designed at Xerox PARC. And they had the following problem. They were designing a distributed system in which the devices were what were called weakly connected. Weakly connected meant that they would sometimes be connected to the network and sometimes be disconnected from the network. Okay? So if the device is itself not even connected to the network, then clearly there is no way to implement consistency, because I cannot propagate a change to a device if it's not even connected. Right? So they said this notion of being weakly connected means none of these guarantees that we can study can be implemented in the system. So we have to think of a new approach. And they came up with the idea of eventual consistency. Okay? So this notion of weakly connected devices is still common today. Okay? So you can think about laptops, right? So you can have a laptop, it's connected to the Wi-Fi network. You close the laptop, take a bus home. While you're taking the bus, your machine is disconnected. It's not connected to any network. So if it was part of any system, maybe it is trying to upload something to the cloud system can't send it any updates by definition because you're not even connected, right? So in many of these cases, weak consistency in the form of eventual consistency is the only thing you can do, because remember the cap theorem where I said if you're disconnected from the network, you can't give guarantees. So that same thing is true here. I can't provide guarantees if the device is not connected. I can't even send messages to it. Right? So that's how this came about. But then they said, how do we implement this notion of eventual consistency? Okay, so this is where this notion of epidemic protocol comes about. Right? So this basically, as the name epidemic suggests, this is how diseases spread. Right? So diseases essentially spread, infectious disease at least, through what is called pairwise interaction. Right? So maybe you're sick. Okay, you go and you shake hands with a friend and you pass on your germs, or you go and cough near somebody, you pass on your germ. They get sick, they do the same thing, they pass on the germ. Right? So that's how diseases, infectious diseases spread. Same thing is true of how we will spread updates. Okay, so from our perspective, updates are something we want to spread. They are like germs. We want to spread them as quickly as possible to everyone in our network. Right? So if a device has an update, it's called that it's said to be infected. Right? Meaning that it has an update, it wants to spread it. And how is it going to spread it? You will do pairwise exchange. Okay? The infected store will try to contact some other machine and say, do you have this update? If the machine says no, so you'll just say, here, I'll give you this new copy. Now you have that update. And then that machine gets infected. It will do the same thing. It will contact some other machine at random and say, do you have the update? If the answer is yes, there's nothing to do. Otherwise, you will actually send that update. Okay? So that's the basic, very high-level idea of epidemic protocol. You use pairwise exchange, okay, to do this, and you will see this is how cloud systems also work. Right? So your machine and the cloud server are pairs. Okay? Whenever your machine contacts the cloud, your machine asks the cloud, do you have any files that have changed on the cloud? And you pull them down, and the cloud system asks your laptop, do you have any new files? If so, you upload them. Right? And then you basically spread the updates, and other devices will do the same thing. Okay? The general concept of epidemic protocol, there is no centralized cloud. You are just doing peer-to-peer exchange of information, right? And just spreading the updates to as many machines as possible. Okay? So there are two techniques that I will talk about that implement the exact same idea. One is called anti-entropy. The other is called rumor mongering, also called gossip. Okay? So epidemic protocols in some literature are also called gossip protocols because they are very similar in how either rumors spread or diseases spread. But let's start with anti-entropy. Okay? So it's peer-to-peer exchange to spread updates. A server P is going to pick another server Q in our distributed system at random. Okay? Randomly, you say pick a server Q, connect to the server, and then you can do one of three things. you can push any infected data to the other server. P can say, I have some infected data, is updates, you push it. Okay? You can pull. You can say, ask you, do you have any new information? Is there any infected data? You pull that data. Okay? Or you do both. Okay? You push and pull. Okay? So you are randomly either going to push, pull, or you do push and pull and exchange information. Okay? And this process will repeat. Okay? Then after some time, P will pick some other machine, do the same thing. Q will pick some other machine, do the same. And eventually, all the data that has been updated will spread because you are randomly connecting to other machines and either pushing and pulling information. Okay? There's no guarantee on how long this will take because everything is randomized. Right? It may take a long time to connect to some machine that has never seen an update because randomly nobody connected to that server to push or pull update. But eventually someone will, and that update will spread. That's the basic idea. Right? So essentially, this is called anti-entropy. Okay? Just randomized exchange where you have two pairs just exchanging information. Okay? Rumor mongering is very similar. It's also called gossiping. So just as I talked about diseases spreading, think about how rumors spread. Right? So maybe you learned about some hot news thing that you want to tell everyone. Okay? So what is that you will do? You will talk to all of your friends and you will immediately tell them I learned about such and such things, and then you will try to push that rumor, and then they might do the same thing and so on. Okay? So while the rumor is hot, everyone is trying to tell other people saying this is what I learned, and so this rumor is going to spread very quickly. But after a while, you will stop spreading the rumor. You'll say, I told everyone, I think everybody knows by this time, so I'm not going to tell anyone anymore. Okay? Which means that from a rumor mongering standpoint, that after every time you spread that rumor, there's a probabilistic backoff, which says, do I believe I told everybody that needs to know, and should I start spreading the rumor? If so, then you will just stop and then you will not spread the rumor anymore. But others might continue to do that until they all back off. Okay? So after every time you tell somebody, you toss a coin, okay, with some probability P. Okay, let's say coin is going to say heads with some probability P and tails with probability 1 minus P. It's not 50-50. We'll assume that it's different. Okay, so some small probability P, it will say heads and you'll say I stop. I think is up. So that's what you will do. So you'll have randomized back off to when you stop spreading your rumors. Okay. So that is called rumor mongering or gossiping. So in this case, what you will see is if everyone stops spreading the rumor, but there are still some nodes that never heard from you, they will never get the update. Okay? Unlike anti-entropy, where there is no stopping, you keep spreading this over and over again. In rumor mongering, there is some probability you will stop and everybody else stops, and some nodes never see the update to begin with. Okay? So in this case, eventual consistency is not fully guaranteed. It depends on the probability P of stopping. Okay? And the smaller that probability, the more the chances are you will spread it before you stop, but that probability can be tweaked and some nodes may never see it in this case. Okay, so that's how rumors are anyway. Right? You can't guarantee that a rumor is going to spread and everybody is going to hear. Maybe some person does not hear it because nobody told them, and then everybody stopped talking about it. Right? So this is a case of eventual consistency where you will not guarantee that the rumor will spread. In fact, there's an equation here which I will not derive, but you will see that there is a exponentially small probability with which you will never see an update because everybody stopped spreading it. Is that clear? Oh.
First algorithm, does push and pull happen in timing order? Otherwise, new updates can be replaced by all updates.
Push and pull happen in same order. So is that the question? Push and pull happen in a certain order? So the assumption here is that you have times to this. You have to have some way to know what is an update and whether you have a newer version or some others have a newer version. So simplest example is you have timestamps on files, and we'll assume you use NTP or some clock synchronization. So clocks are synchronized. So you can simply, if these are file searches, you can look at file update times and say, do I have a newer version or do you have a newer? Or you can add version numbers. Okay? Just as source code control has version number, right? So you can figure this out. So you have to have some way to know whether a file is newer or older. In that case, it doesn't matter whether you do push or pull. Okay? Whether you do push or pull, you know who has newer information and you can spread. And you can use this to spread multiple data items at once. It doesn't have to be one data item. You can have a set of updates to many different data items. that are all spreading this way. Each data item is like an infection that's spreading, a distinct infection, right? But you can have more of them going on at the same time. Yes.
So if rumor mongering is not eventually, why would we want to use it?
Okay. The question is, if rumor mongering is not eventually consistent, why would you want to use it? So you can think about the other aspects. Anti-entropy never stops. Okay? Let's take a case where updates have stopped. No one is updating anything. Anti-entropy will still require every machine to contact every other machine, and both machines say there's no new information, so there's nothing to do. Then you contact another machine. So you'll waste messages there if there are no updates. Okay? If there are always updates in the system, then it's fine to have anti-entropy because there's always some useful information being exchanged. Okay? In rumor mongering, there is a stopping probability. So if updates stop, eventually message exchange stop. You're not wasting network overhead contacting machine. Right? So that's the real trade-off between the two. But there is always a risk someone will not receive this. Okay. All right. So there's one more thing I want to mention. Then we will end. Okay? That's essentially how are you going to delete data when you have epidemic protocols or consistency. Okay? So as it turns out, deleting of a data item is also a type of an update. Okay? You can go and update file by writing to it. That's an update. Deleting a file is also an update where you removed all the data from the file and file itself is gone. Okay? So we will assume the delete is a special type of an update as far as we are concerned, where we removed all of the data. Okay? Now, the question is, how are you actually going to spread the fact that you deleted a file? Right? So let's say you had a file. While it was being updated, you could compare it on another machine and say, I have a newer version, here are my updates and so on. But let's say you as a user just deleted the file. Okay? The file is gone from your folder. Now, if you are using anti-entropy, your machine is contacting some other machine saying, what is the information that I have missing? And you say, I don't have file A, but that machine has file A. So you will now assume that that file has appeared and you will get it back. Okay? So your deleted data item has now reappeared because you assumed it was gone, but when your machine contacted some other machine, it saw a file that it didn't have. Okay? And then suddenly you bring that file over and say your deleted data is returned on your machine. Okay? So if you just trivially delete a file, okay, and assume that that deletion is going to spread, it doesn't spread. In fact, the file actually reappears because there is no information kept that there was a deletion. Okay? So the way you are going to spread deletion is what we call death certificates, which means that when you delete a file, it's actually gone from your file system, but you keep a record. It's like a death certificate saying, I had this file, it actually got deleted. That's my final update to the file. Okay? And now, when you compare this with some other machine, your death certificate will always have a later timestamp. So you will tell that machine saying, okay, the file was actually deleted. So you'll start spreading the death certificate through the system. And then every machine will start deleting it from their system and then start spreading that death certificate everywhere else. Right? So basically, this is how you're going to implement a delete. You can't just simply delete the file and assume that you can synchronize it because there's no record that there was ever a deletion. So when you delete a file, these systems have to keep track of that, the fact there was deletion, and then spread that information and then ensure that the file gets deleted from all of the machines. Okay? So this is how you will actually take deletions and as an update and spread them around using epidemic protocol. Okay? But there's still one problem. Okay? After a long period of time, lots of files would have gotten created and deleted. So there'll be lots of death certificates sitting in the system. Okay? Because if you remove a death certificate, there might still be some machine because eventual consistency that hasn't seen it, and then that machine still has the file and it will reappear. Okay? So you might have to wait a long time to clean up the death certificates, but you better be sure when you delete your death certificates from all the machines that every machine has seen the update. Because even if there's one that didn't see it, your file will reappear. Okay? So when to delete that certificate becomes its own problem. Yeah? So now clearly this doesn't take up too much resources, so you can keep it for long periods of time, unlike files, but there has to be some policy by which you clean it up, but with the assurance that your file doesn't reappear. Okay? Yes.
even if the same record is being written as P by another node, that
Yeah, so I don't fully understand your question, but you are asking if the file is modified, you are looking at timestamps to figure out how to propagate the chain. Okay? That's absolutely true. What I was saying is the file was modified for some period of time and then somebody has deleted the file. So then now the file is gone from one machine. Okay? So that is my most recent update to the file is let's remove the file completely. Okay? Now, if you want to synchronize that, you have to propagate that information and every machine has to delete the file. Okay? But as far as the machine where the file was deleted is concerned, what does deletion do? It just simply removes it from my directory. The file that there's no trace of the file at that point. Right? So if I compare my directory with some other machine's directory saying, do you have any updates? You will see that you don't have this file because it was deleted. The other machine still has the file. Okay? And there's no record that there's any deletion. So it will look like the file got created to begin with. This is how file creation would work as well. I create a new file, I compare directories, and I say, you don't have this file, I push that. That's the same thing will happen again. And the file will reappear. Right? So this is why we need to keep extra information, which we'll call death certificates to say it was deleted. Okay? All right. Any other questions here? We are going to end a little bit early, but we are done with consistency. Okay? And as I said, we started with strict consistency. We looked at a whole sequence of them. And then we ended up with eventual consistency and epidemic protocols, which, like it or not, is what many of these systems, including cloud systems, implement. Or anything else tends to be harder. Okay? Except the world of databases, where you don't want to be eventually consistent. If you have bank databases and things like that, then you will have real correctness problems. That is where you pay the price. But for many other systems, you just go with something much, much weaker like this. Okay? All right. So let's stop here and then we'll continue next time on Monday.